welcome to another module in this massive open online course. So, we are looking at the sampling of an analog signal to extract samples from it to convert it to a digital signal, alright, and we have said that the signal can be sampled by multiplying it by an impulse train, alright, which is termed as ideal sampling, alright. So, let us consider our impulse train, which is given by G delta t equals summation this is your summation n equal to minus infinity, that is summation n equal to minus infinity to infinity delta t minus n ts, where ts is the sampling interval, alright, which is basically the time interval between the successive sampling instants. Okay. Delta is of course the Dirac delta function, and this is basically we have our sequence of impulses, a train of impulses at every multiple of Ts. So, we have impulse at Ts, we have impulse, so this is our impulse at Ts, we have impulse at 2 Ts, we have impulse at 3 Ts and so on, and of course, we have impulse at 0, we have an impulse at minus Ts, minus 2 Ts, etc. And now what we want to do is we want to find the spectrum G delta f, that is the spectrum G delta f, which is basically your spectrum of G delta t. Okay, we want to start with that towards eventually find the spectrum of the sampled signal. Now, you will see that this signal, if you look at this signal, this impulse train, correct, this impulse train, you will realize this is a periodic signal. Correct. The impulse train is a periodic signal since there is one impulse every Ts. So, you have impulse at Ts, impulse at 0, impulse at Ts, 2 Ts, minus 2 Ts and so on, alright. So, this is a periodic signal with period Ts. Okay. So, this is a periodic signal with period equal to Ts. Okay. So, in one period, let us say this is basically your xt or your G delta t equals basically delta t 0 less than equal to t less than Ts, alright, this is the signal, and therefore, since this is periodic, we can find the discrete Fourier series representation. Since this is periodic, one can find the discrete Fourier series of G delta t. Okay. So, let us express G delta t. So, G delta t can be expressed as summation, well, k equals minus infinity to infinity C k e to the power of j 2 pi k f s t where Fs equals 1 over Ts. The sampling frequency is the fundamental frequency, alright. Fundamental frequency is 1 over time period, correct. The fundamental frequency is 1 over the time period. The time period is nothing but the sampling interval, right, sampling interval, that is Ts. Therefore, the sampling frequency Fs itself is the fundamental frequency, okay. So, the fundamental frequency equals the sampling frequency, alright. And further, now we have to find this coefficient Ck, and you can see that this coefficient, each Ck equals, well, 1 over Ts. We know the expression for Ck, 1 over Ts integral 0 to Ts, correct, G delta T or we can make it from minus Ts by 2 to Ts by 2 G delta T dt, which is equal to 1 over Ts minus Ts by 2 to Ts by 2 delta T, G delta T e to the power of minus j 2 pi k f s t e to the power of minus j 2 pi k f s t dt, alright, where we replace G delta T by delta T in that interval minus Ts by 2 to Ts by 2. Now, the integration with multiplying by delta T is very simple, that is when I multiply a function by delta T and integrate, that extracts the value of the function at t equal to 0. So, this is simply e to the power of minus j 2 pi k f s t evaluated at t equal to 0, that is simply 1 over, that is simply 1. So, this quantity is simply 1 over Ts into 1. So, 1 over Ts. So, each Ck has a very simple expression, each Ck, this is the kth coefficient in the discrete Fourier series kth coefficient in the discrete Fourier series of G delta T. That is your basically your Ck. So, we evaluated each coefficient Ck as 1 over Ts, and therefore, now the discrete Fourier series representation of this impulse train is basically given as, I have G delta T equals summation k equals minus infinity to infinity 1 over Ts e to the power of j 2 pi k Fs e to the power of j 2 pi k Fst, which is also basically, you can write it, since 1 over Ts is common. So, you can take it outside of the summation, 1 over Ts k equal to minus infinity to infinity e to the power of j 2 pi k Fs t. This is your discrete Fourier series. This is basically your discrete Fourier series. This is basically the discrete Fourier series representation, okay, correct. And now, from this discrete Fourier series representation, we can find the Fourier transform. So, from this, find the Ft or the Fourier transform, and that is simple. One can extract the Fourier transform because e to the power of j 2 pi k f s t, if you look at e to the power of j 2 pi k f s t, e to the power of j, that is nothing but an impulse. This Fourier transform of this is an impulse at kfs, correct. Fourier transform is an impulse at kfs. Fourier transform or basically spectrum is an impulse at kfs, which means now the Fourier transform of this is basically g delta t is basically each Fourier transform of each is basically an impulse delta f minus k f s. Therefore, the Fourier transform g delta f, which is basically the Fourier transform of g delta t, is basically, so if you look at g delta t and let us say we consider its Fourier transform capital G delta f, that is simply summation k equal to minus infinity to infinity 1 over, well, there is a 1 over T s each e to the power of j 2 pi f k f T s k f e to the power of j 2 pi k f s t has a spectrum delta f minus k f s. Okay, and f s, remember f s is basically 1 over T s. So, this is basically nothing but 1 over T s summation k equal to minus infinity to infinity delta f minus 1 over T s. Okay. And therefore, you can see something very interesting, which is basically if you look at this summation, if you look at this summation 1 over T s summation k equal to minus infinity to infinity delta f minus 1 over T s, this is basically another impulse train. Now, you can see that this, except for the scaling factor of 1 over T s, this is basically another impulse train, and this is a train of impulses in the frequency domain. So, alright. So, we have started with a train of impulse train in the time domain, and what we are seeing is its Fourier transform or spectrum is basically an impulse train in the frequency domain, impulse train in the frequency domain. Is an impulse train in the frequency domain. Further, the spacing between the impulses, that is each impulse, I am missing a factor of k over here, yeah, this is f minus k over T s. So, spacing between impulses equals f s equals 1 over T s. Remember, spacing in time equals T s, the impulses are spaced at, because T s is the sampling interval, alright. So, the impulses are spaced T s apart, but in frequency impulses are spaced. So, spacing in frequency equals, spacing in frequency equals, this equals 1 over T s, alright. So, spacing in so as the spacing in time is T s, spacing in frequency is 1 over T s. So, basically as the sampling interval T s increases, the spacing in time increases, the spacing in frequency, that is 1 over T s, decreases, because 1 over T s is the sampling frequency. As the sampling interval increases, f s, that is the sampling frequency, decreases. So, spacing in frequency is the sampling frequency, alright. As sampling time, sampling interval is increasing, the sampling frequency is decreasing, therefore spacing in the frequency domain is decreasing. And conversely, as the spacing in the vice versa, right, as the spacing in the time decreases, that is you are sampling at finer at finer and finer interval, right, that is Ts is decreasing, the sampling interval Ts is decreasing, which means the sampling frequency Fs is increasing, the spacing in frequency increases, alright. So, this is spacing in frequency is Ts equals 1 over Ts equal to Fs. So, you can note that as spacing in time increases, spacing in the frequency domain decreases, okay. As spacing in time increases, spacing in frequency domain increases, and vice versa, as spacing in time decreases, as spacing in time decreases, spacing in the frequency that basically increases, alright. So, that is basically, it means that as you are sampling finer and finer in time, that is Ts is decreasing, the spacing in frequency, that is the sampling frequency Fs is increasing, therefore, the spacing between these successive impulses of the impulse train and the frequency domain is increasing. Now, let us look at what is the Fourier transform of the sampled function, alright. So, now we are in a position to look at the Fourier transform of the sampled function. So, we want to look, we have found the Fourier transform of the impulse train. Now, Fourier transform of the Fourier transform of the sampled analog signal. Now, you can see that will be given as follows. Remember, m delta t or sampled analog signal is simply m of t times g delta t. This is your sampled analog signal. This is your sampled signal, and m of t is the original analog signal. Your original this is your original analog signal. And now, if I look at the Fourier transform of this, correct, that is very simple. M delta f is the Fourier transform of m delta t, that is the sampled signal. This is equal to, now you can see mt let us say has a Fourier transform m of f, and g delta t we know has a Fourier transform g delta f. This will be the convolution between the Fourier transform m delta f, mf and g delta f, because multiplication in the time domain is convolution in the frequency domain. So, multiplication in time becomes convolution multiplication in time becomes convolution in the frequency domain. Therefore, m delta f, that is the spectrum of the sampled signal, equals m of f convolved with g delta f. G delta f we have seen is 1 over Ts summation, that is 1 over Ts summation delta f minus KFS, and 1 over Ts is also equal to, remember 1 over Ts is also equal to Fs. So, this is basically your convolution with Fs times summation k equals minus infinity to infinity, correct, k equals minus infinity to infinity Fs delta f minus k Fs, where Fs is the sampling frequency, and this is equal to, well, Fs summation k equal to minus infinity to infinity Mf convolved with delta k Fs, which is Fs now k equal to minus infinity to infinity Mf convolved with delta f minus k Fs. Remember, this is nothing but Mf minus k Fs. So, this is Mf minus k Fs, that is your M, that is your M delta f. M delta f is basically k equal to minus infinity to infinity, M delta f is Fs summation k equal to minus infinity to infinity Mf minus Mf minus kfs, Mf minus kfs, Mf minus kfs. That is, what you are doing here is something very interesting. Alright. First, let me elaborate. The property that we have used here again is something that should be very familiar to you, that is Mf convolved with delta f minus f naught simply shifts Mf to f naught. So, Mf convolved with each delta f minus kfs simply shifts each Mf to kfs, and therefore, now what you are doing is you are shifting this spectrum Mf to each kfs, alright. So, for at each kfs, that is k times multiple of the sampling frequency Fs, right, you have a copy, alright, of this original spectrum Mf. So, now you are shifting this spectrum Mf to each kfs and you are summing all these copies. So, the spectrum of the sampled signal will be the sum of the copies of the original spectrum Mf shifted to every multiple of the sampling frequency Fs. Okay. So, what you are seeing here is something very interesting. What you have is, this is the spectrum of sampled signal equals sum of all copies of the original message spectrum Mf shifted to every KFS, where KFS, remember KFS is kth, basically this is the kth multiple of the sampling frequency. So, this is a sum of all copies of the message spectrum shifted to every KFS, which is very interesting. So, you have the original spectrum Mf, now we are shifting this to each KFS, right, each multiple of the sampling frequency, each integer multiple of the sampling frequency Fs. Therefore, you are making an infinite number of copies of the original spectrum Mf, and then you are adding all these copies. Now, let us see in the frequency domain what this corresponds to. So, you have your original spectrum Mf, okay. So, let us say you have your original spectrum. This can lead to something very interesting in the frequency domain. You have your original spectrum Mf, correct. You have your original spectrum MF, okay. Let us say the maximum frequency is FM between minus FM. So, this is your original message spectrum MF. Now, let us draw here the sampled spectrum. So, we are going to have, well, we are going to have the original message spectrum intact, that is going to be intact. So, we are going to have the original message spectrum that is going to be intact, and so that is going to be, this is going to be MF. In addition, at Fs you will have one copy at Fs, correct. So, this is the copy at 0. In addition, you will have one copy which is shifted to Fs, correct. So, that will be, that copy will be, so this point is your Fm. Now, there is a copy at Fs. So, this point naturally is Fs plus Fm, and this point is interesting. If you look at this, this is Fs minus Fm. Now, there can potentially be an overlap in this region. These two copies, so this is your MF, this is your MF minus MF. So, there can be an overlap between these two copies. So, MF, now if you can see this corresponds, this is interesting. So, there can be an overlap, and the overlap leads to distortion. So, you have a copy of the original spectrum, there is another, you have the original spectrum at 0, there is another copy shifted by Fs. When you take the sum, these two copies can overlap, and therefore, once you sum, that can lead to distortion, alright. And this can cause distortion of the sample, that is the spectrum of the sampled signal is not similar to the spectrum of the sampled signal, that is m delta t, that is m delta f, is not similar to the spectrum mf of the original signal. It is a distortion version of the distorted version of the spectrum of the original signal mf, alright. And when does this arise? This distortion arises if there is an overlap. Now, realize that this distortion arises when, you can see when will there be an overlap? There will be an overlap when Fs minus Fm is less than Fm. Fs minus Fm is less than Fm, which implies Fs is less than twice Fm. So, the spectral overlap. So, this is a very important and very interesting condition, the spectral overlap, right, spectral overlap between these different copies of the spectrum shifted by the various integer multiples of Fs will occur if the sampling frequency Fs is less than twice the maximum frequency Fm of the original analog signal, alright. And therefore, and this distortion which occurs because of the spectral overlap is termed as aliasing, okay. So, this distortion which occurs because of overlap between copies of spectrum shifted by multiples of Fs is termed as aliasing. Is termed as aliasing. This is termed as aliasing. So, this distortion which occurs because of this overlap, this distortion is termed as aliasing. And aliasing occurs if Fs less than twice Fm, that is aliasing occurs, and this is a very important condition. Aliasing occurs if Fs less than twice Fm. That is another way of stating this is basically sampling frequency is less than twice the frequency of the your sampling frequency is less than twice the maximum sampling frequency is less than twice the maximum frequency of the signal being sampled, that is twice the maximum frequency of your MT. Therefore, to avoid aliasing we need Fs greater than Am. Therefore, to avoid aliasing or aliasing distortion, we need Fs greater than or equal to twice Fm, and this is termed as the Nyquist. This is termed as the Nyquist criterion for sampling to avoid aliasing. This is termed as the, this has many names. This is termed as the Nyquist criterion. This is termed as the Nyquist criterion or your Nyquist this is termed as the Nyquist criterion or the Nyquist sampling theorem, which basically says that to avoid aliasing which arises from the overlap of the spectral copies or the shifted spectral copies at the different multiples of the sampling frequency Fs, one has to sample at a sampling frequency Fs greater than twice Fm, where Fm is the maximum message frequency, alright, maximum message frequency, or Fm you can think of it also as the bandwidth of the original signal. You have to sample at great sampling frequency greater than twice the bandwidth. This is termed as the Nyquist criterion or the Nyquist sampling theorem, which states that to avoid aliasing one has to sample at Fs greater than twice Fm, alright. And therefore, what we have seen is something very interesting, that the original sampled, the sampled signal can be a distorted version of the original signal, and that distortion occurs because these different spectral copies, that is the spectrum of the sample signal, which comprises of the sum of the spectral copies which are shifted by different multiples of the sampling frequency, various shifted by all possible multiples of the all possible integer multiples of the sampling frequency Fs, alright. And because there can be possible overlap between these spectral copies, that results in distortion, which is termed as aliasing. Distortion occurs if Fs is less than twice Fm. Therefore, to avoid this distortion we need sampling frequency greater than or equal to twice Fm. This is termed as this condition, alright. This result is basically termed as the Nyquist criterion. This criterion or this condition required, that is the minimum sampling frequency required to avoid aliasing, is termed as a Nyquist criterion, and this result is termed as the Nyquist sampling theorem, alright. So, we will stop here and look at other aspects in the subsequent modules. Thank you.